Welcome, friends. Welcome to this academic program. In last lecture, we have discussed about the transmission line conductors, transmission line towers. Today, we shall start our new topic, which is regarding transmission line parameters. As we can already know, as we are aware that there are four parameters are there. Number one is R, then second one is L. These two will constitute series impedance, which is R is equal to J omega L. Third one is capacitance and fourth one is conductance. These two will constitute shunt admittance, which is equal to G plus JB. Now, out of these four, inductance is the most dominant parameters. So, as we are told that there are four parameters, out of them G is not considered due to many reasons. So fundamentally there are principally three parameters are there. Now resistance value should be low in order to flow high amount of current. One important feature of the transmission line is that its X by R ratio, it should be greater than or equal to 10. If the R value goes high, then that is not good for our system, and that power system is called ill-conditioned power system. So with high value of resistance, we say that that power system is called ill-conditioned. And of course, the value of resistance is depend on the weather. R goes high in summer, R goes low in case of winter, as temperature is a sensitive factor in determining the resistance value. Now coming to the most dominant parameter of transmission line, that is inductance. The definition of inductance is flux linkage per current. So this is psi by I. Unit should be Henry. Now, suppose we have a solid conductor like this. So, what will be the equivalent inductance? If the current carrying this conductor is carrying a current I, then what will be the inductance of this conductor? That we shall see shortly. Now, as the current is flowing, it will produce a magnetic field. It will produce a magnetic field that will create a flux. That flux will link this current internally as well as externally. Internally as well as externally. That means any internal flux will surely link with this current. However, the external flux will also linking with that current. So, inductance value, that is the flux linkage, okay, that can be seen as a effect of two flux linkage, that is internal flux linkage and another component is external flux linkage. So, overall inductance of the solid conductor can be seen as a result of these two effects, internal flux linkage and external flux linkage. That we will see now what will be the inductance of a solid conductor. So we shall see shortly. So let me use a different ink. So what is the inductance of a solid conductor? Let us say we have a conductor of radius r. Let us say we have a conductor of radius r. Now, to understand the internal flux linkage, we will assume something. We will draw a circular shell of thickness x. Circular shell of thickness x. So this thickness is dx, which is located at a x distance. Which is located at a x distance. Now, which is located at a x distance. So, what will be the magnetic field intensity Hx at a distance, that is line integral of that magnetic field, that means that should be equal to current enclosed within that. So this is the equation is obtained by the famous law. It's called Ampere's circuital law. Ampere's circuital law. What is the statement? That is the line integral over a closed path of a magnetic field that will be is equal to the current enclosed within that path. Now, what is dx? So, if we consider this is the shell and this is a small length dx, so if we integrate over this line, so it should get integration dx should be 2 pi into x, hx into 2 pi x. So that is the integration of dx. Now what will be the I enclosed? Now I enclosed is the current density, that is I by pi r square, into the current enclosed within that area, that means pi x square. That means it is pi x square. Okay. So from here we can write Hx, that is equal to I by 2 pi r square into x. This is Hx. Now from here, if the magnetic field intensity is this, so what will be the magnetic flux density? So magnetic flux density at x, magnetic flux density at x, bx, that will be equal to mu naught mu r into hx. This mu naught mu r collectively called mu, which is called permeability of the medium. Permeability of the medium. So here we have mu naught is equal to 4 pi into 10 to the power minus 7 Henry per meter. And of course, in this case, we will assume mu r is equal to air for air. So what we have got here is that, so therefore we have Hx, that is equal to Ix by 2 pi r square. So from there we have Bx, that will be mu naught. Mu naught is equal to 4 pi into 10 to the power minus 7. Mu r is equal to 1. So Hx, now it should Hx value, so I into x by 2 pi r square. So this will be equal to, this 4 pi and 2 pi gets cancelled, so it will be 2 into I x by r square along with a term 10 to the power minus 7. This is the Hx for you, Bx for you, flux density. Now if you have a flux density Bx, then what will be the flux? Magnetic flux. Magnetic flux at x, d phi x, magnetic flux at x, that will be is equal to magnetic flux density into area, into area. Now what will be the area of this shell? What will be the area of this shell? Now in this diagram we are only considering the cross sectional view. We are only considering the cross sectional view. So due to that fact, here length of this conductor is always considered to be the unity. So this shell having a cross sectional area is dx into 1. Having a cross sectional area is equal to dx into 1. So that is what we are using over that expression. So magnetic flux density we have 2I x by r square along with this term 10 to the power minus 7. This is magnetic flux density into area is dx into 1, because we are considering only cross sectional view, only cross sectional view. So length of the conductor becomes unity. So therefore d phi x, that will be equal to 2 pi x dx by r square along with this term 10 to the power minus 7. So if this flux is there, so what will be the flux linkage? So internal flux linkage, internal flux linkage, that is d psi internal, or d psi x, that will be equal to d phi x, that will be into pi x square by pi r square, because whatever be the internal flux, that will be linked only up to this. So this is defined by pi x square by pi r square within this shell. So this is what we get. So d phi x is 2 into I into x dx by r square, that multiplied with pi x square by pi r square. So of course with the term 10 to the power minus 7. So we have pi gets cancelled. So we have 2 into I into 10 to the power minus 7 by r to the power 4, along with we have x cube dx. So total internal flux linkage. So total internal flux linkage. Total internal flux linkage. Now we should integrate this expression 2I into 10 to the power minus 7 by r to the power 4, integration x from 0 to conductor radius r, x cube dx. So it will come out to be, the integration come out to be x to the power 4 by 4. So if you put the limit, so this expression will come 2I into 10 to the power minus 7 by r to the power 4 into r to the power 4 by 4. So altogether we will get the result I by 2 into 10 to the power minus 7, 10 to the power minus 7 I by 2 into 10 to the power minus 7 Weber turn per meter. So this is the internal flux linkage. So now coming to the external flux linkage. Now coming to the external flux linkage. We will derive something similar. So let me consider this is the conductor having the same radius r. Now we will consider two spheres or two planes situated at a distance d1 from the center and d2 from the center. Of course, d2 is greater than d1, and in between we will assume a circular shell. In between we will assume a circular shell of thickness dx. Circular shell of thickness dx, which is located at a x distance. So we shall proceed, we shall adopt a similar procedure for this. So what is Hx as per Ampere circuital law? Hx into dx, that will be I enclosed. Of course, we need to take the integration over a closed circle. So Hx into, now this dx integration becomes 2 pi x. This integration becomes 2 pi x. This integration becomes 2 pi x. Now what will be the I enclosed? Now current is flowing through this conductor. So now this time for external flux linkage, entire current will be enclosed by this path. So I enclosed in this time, it is only I. But previously it was I into pi x square by pi r square. Previously for internal flux linkage, the current enclosed was given by this. But in this case it is only I, because this entire amount of current is enclosed by this path. So from there we can say Hx is equal to I by 2 pi x. So from there Bx, that is the magnetic flux density, that will be is equal to mu naught I by 2 pi x. We consider mu r, that will be is equal to 1 for air. Once done that, we can write Bx, that is equal to 4 pi into 10 to the power minus 7 into I by 2 pi x. So we have 2 into 10 to the power minus 7 I by x. So then what will be the flux linkage? What will be the flux linkage? We have flux linkage, that is d phi x for external cases, that will be is equal to Bx into area. Again, area is nothing but Bx into dx into 1. So we have 2 into 10 to the power minus 7 I dx by x. So once we got the flux link, sorry, this is not a flux linkage, this is flux. This is flux. Okay. Now once we have the flux, we are going to get what is the flux linkage d psi x for external effect. Now this external flux will link all the current, so it is d phi x multiplied by 1. So since all the flux will be linking to the current, so it is straight away multiplied with 1. 2 into 10 to the power minus 7 into I into dx by x. So therefore total flux linkage can be found out for external effect. So it will be 2 into 10 to the power minus 7 into I. Now integration dx by x from x starting from d1 to d2. So as a result, this integration is found to be 2 into 10 to the power minus 7 I into ln d2 by d1. Now this d2, you see from the diagram, this d2 and d1, this d2 and d1 are the any 2 points outside the conductor. So d1 can be represented as or can be approximated as r, which is the conductor radius, and d2 can be approximated something like d, that is capital D becomes the distance from one conductor to the other conductor. So that approximation we should use in this case. So we are approximating d1 nearly equal to r and d2 nearly equal to capital D. So from there we can say external flux linkage, that will be equal to 2 into 10 to the power minus 7 I ln d by r. So what will be the total flux linkage? Total flux linkage. Now total flux linkage can be found to be by adding internal flux linkage as well as external flux linkage. So what is internal flux linkage? It was half into I into 10 to the power minus 7, and internal, so let me investigate what was internal flux linkage. Internal flux linkage is this I by 2 into 10 to the power minus 7 Weber turn per meter, and external flux linkage is found to be by this formula. So now external flux linkage is 2 into 10 to the power minus 7 I ln d by r. With that we take 2I into 10 to the power minus 7 common. So we have first term as 1 by 4 and second term is ln d by r. So with that 1 by 4 can be written as ln e to the power 1 by 4 plus ln d by r. So this overall expression inside this square bracket can be written as ln d by r into e to the power minus 1 by 4. Which is represented as 2 into I into 10 to the power minus 7 ln d by r dash. What is r dash? R dash is equal to e to the power minus 1 by 4 into r. Now once we evaluated this, it will comes out to be 0.7788 into r. So this is a very interesting result. One can take the conclusion from here is that once an inductance is being calculated, conductor radius should be treated as r dash, which is equal to 0.7788 r. It never be taken or never be considered as full value of r, but to consider a small fraction of R, that is 0.7788 R. This R dash is called geometric mean radius. So this is very interesting. So we have inductance L, that is psi by I. So that will be is equal to 2 into 10 to the power minus 7 ln d by R dash. What is d? D is the distance from one conductor to the other one. And what is R dash? It is called GMR, that is geometric mean radius, which is equal to 0.7788 into R. What is the meaning of this expression? Because you see, flux is linking internally as well as externally. So when these two effects are considered, the equivalent resistance is formed and found to be some portion of or some fraction of the overall conductor radius. So please remember this fact. When you calculate the inductance of a transmission line, you should always treat R as R dash. So if the conductor radius is, let us say it is given 1 centimeter, you in your calculation you should use 0.7788 centimeter. So this is the formula for inductance of a solid conductor. Now so as it can be seen, internal flux linkage is this, external flux linkage is this. So we have the total inductance is 2 into this value, Weber turn per meter, and finally we have inductance of a solid conductor is given by 2 into 10 to the power minus 7 ln d by R dash. Now if you consider the return conductor, this formula is found to be 4 into 10 to the power minus 7. Okay, so this means it's double. Okay, so you need to consider the return conductor, then this formula becomes double. So in nutshell, what we have got, inductance is found to be 2 into 10 to the power minus 7 ln d by R dash. With this, I am ending my lecture here. From next lecture, we will consider more realistic conductor. That means what will be the inductance of a stranded conductor. Now we shall use this formula as our base. From this, we shall discuss what will be the inductance of a stranded conductor. Thank you.